Hi, I'm Melanie Beechwood with Northeastern University. I'm in the computer vision class of spring 2026. And we're going to do a very short lecture on deep was published a method for scalable semantics and deep learning done back in 2023 for methods in ecology and evolution. This was to help researchers on coral reefs be able to maintain and understand coral reefs better in something that is very, very labor intensive and can be very expensive for equipment and computation, and able to do that with one dive, a consumer grade camera, consumer grade compute, just one GPU, and have really good accuracy with what is currently on the market. So we're going to have to go a little bit quickly on this, but just to give you an idea, so we're going to be hearing me speak about transect lines and ego motion. So a transect line is when they lay a line on the seafloor and the beginning is known on GPS. So they have that. A diver is going to swim with a camera and take a video down this transect line. So the video itself is often known as a transect. The goal of this is to have ego motion. So we have an understanding of motion by having all of these frames coming through this. This is similar to what we saw in SLAM, of the ability to understand kind of where you're at in the world, but we're not going to be using the SLAM algorithm. So that is a little bit about what a transect line is. Now, the full purpose of this paper is to kind of build on computer vision work that's already in existence, doing structure from motion photogrammetry. Now, structure from motion photogrammetry has a lot of overlap in some of our understanding that we did earlier in the course with things like SLAM. So with SLAM, we are doing it live. We get localization, so the where we are, and the mapping of the world at the same time. These need to be very efficient. With structure from motion, these are offline, which means they can be computationally more intensive, and we don't really need to know where we are anymore because we're not currently progressing through that world. We're using it to get a 3D model. So we're only caring about that mapping on the world. But we do want to get a good enough map to potentially bring that 3D world into a visual space, whether this can be used for virtual reality, for animation, all sorts of things. And it has some of the work that we talked about with the Gaussian splatting is kind of in this space as well. So we're doing the photogrammetry. They're also using it to cover segmentation and classification of corals in that reef. Given the brief time that we have together, we might touch on this a little bit, but it is fairly similar to some of the segmentation that we did in class with a classification system that we can briefly go over. But we're going to focus today on how they did this structure through motion. So the existing structure through motion mapping techniques are very brittle. They often need highly curated, high resolution images, reconstruction, or they can struggle to get full 3D models. Often these can also be really difficult with cameras, the consumer grade cameras, due to the poor water quality and image quality. It's in water, you've got distortions, it could be cloudy one day, you could have a lot of fish going on. There's a lot that happens in a water environment that makes this particularly tricky. So before we get into how they did it, I want to give you a small example here. On the right with Metashape is an existing technology for underwater structure through motion. This is actually what they were calling out there, that on this is the transect line, and then these are markers that they put in to be able to directly compare. When we zoom in, we can still see a lot of the structure, even though this is on a printed. But if there isn't enough images, whether that's because there wasn't enough to really piece it together, like having the ocean without any defining landmarks or poor visual quality or things like that, you get these really kind of failed states in this image. On the left is their methodology. You can see a straight line from the transect that covers the entire thing, so they didn't have any of that kind of patchiness that you saw in the Metashape. And here's the same segment with those same markers. You can already see just from here that this is a much lower res image, but it is fully fleshed out. That's kind of one of the big trade-offs here. Now, there's a lot of interesting work that they did, but I want to showcase some of what they're talking about, because one of the big differences on how they do the structure for motion, so they're using a deep learning based structure from motion. Now, this is not where it sounds like it's a fairly standard setup for a deep learning base. But this is interesting because it kind of reminds me of early on in the class when we had that depth network, that it was kind of similar to this. But this is going to do both depth and post prediction at the same time. And it does this by training this neural network. They're using underwater to try to help adjust it for this situation. It is going to be using a lot of the work that we discussed kind of in when we were discussing SLAM around having this, since they're using a monocular and one camera, instead of doing it from stereo from two things, they're going to do it over a time t, and then calculate that reprojection loss and understand and do that triangulation to figure out where those pose estimates are. And then it's going to do a deep neural network to try to learn how to predict those with respect to that loss. There's a lot of really cool information here, but we don't have a lot of time. So one of the interesting areas in the appendix is that they go into a little bit more about how they did this though. So this is their architecture for their depth and pose estimation neural network. They're using ResNet 34 encoders with a UNet. So remember, we discussed those in a recent lecture. So they have one encoder that does a sequence of 7 images. This one allows them to have poor image quality, be able to do more with it, and kind of help with that features over that time t in this really difficult environment. And this goes in for that sequence encoder. Then they also have one that's a single image encoder, or 2 single image encoders, one that feeds into the depth decoder of a certain one image and a depth decoder of the other. And then all of those 7 are used in that pose transform, which it gets that pose inference, but they're also used as they feed in to these depth decoders to estimate the depth on those single images. I thought was really an interesting way of doing it. All right. We only have another moment left. So just really quickly so you can see it, I'm not going to go into detail of how they did that. So here is a thing of kind of how theirs looks versus some of the existing competitors. They don't do high res, they do lower res, but at low res, they're able to keep a nice clean line, which is really cool. They do discuss why this isn't a spiral if you're curious, but we do not have time to get into it. Now, the second part of this is being able to segment, and there's these live video frames. They do that network prediction, and then they segment, and they have some Grand Tour animations on some of these to understand how it did. You can explore this further onto how they did the segmentation, but here is a list of how they classified these guys. What the sense of giving them is a point cloud that has both the depth as well as the ability to segment and kind of bring this into the world. One of the last interesting points I thought was really fun was they have a way of both segmenting out people and fish to help clean up their 3D image afterwards, as well as the sea. So this is an example here where they really only care about the coral, so they only want this segment. So it segments out that deep sea here and that human, and then those are both masked out in the final. Okay, overall this did really, really well, and they were able to have a good accuracy comparatively to the existing methods, but it's a lot cheaper. You only need one camera, and it can be consumer grade, and only needs one line, which means that they can go, I think they said 100 meters in a dive, meaning that they can do a lot within just one time period. So future work, they do recognize that this is scale free, so if you wanted to do more with that, that would be a future improvement. And yeah, so that's kind of some of the basis of this. Take a look at it. It's a really cool paper. They're continuing to build on this and continuing to build these data sets. They actually just recently released a data set, and they seem like they're doing some really cool work, and it kind of takes a step, all of these things that we've done in class, bundles them together into a new applied way and goes another step further. All right, thank you very much. Have a good day.